Welcome! In this session, we'll tackle LeetCode problem number 356, line reflection. Our goal is to determine whether a given set of 2D points is symmetric about a vertical line. Let's dive in. In this problem, we are tasked with determining whether a given set of 2D points is symmetric about a vertical line. Symmetry here means that for every point in the set, there exists a corresponding reflected point across this vertical line. The input is a list of points, where each point is defined by an x-coordinate and a y-coordinate, both of which are integers. Our goal is to return true if such a vertical line of reflection exists for all points, and false otherwise. To illustrate this concept, let's look at a couple of examples. In the first example, the input points are 1, 1, 1, 1. The output is true, and here's why: the vertical line x equals 0 acts as the line of reflection. The point 1, 1 is mirrored by 1, 1 across this line. Now, in the second example, the input is 1, 1, 1, minus 1. The output is false because no vertical line exists that can reflect 1, 1, 2, 1, minus 1 while maintaining symmetry for all points. These examples highlight the importance of finding a line that works for the entire set, not just individual pairs. Let's consider a third example to clarify further. Here, the input points are 0, 0, 1, 0, 1, 0. The output is true. The vertical line x equals 0 serves as the line of reflection. The point 1, 0 is mirrored by 1, 0, and the point 0, 0 lies directly on the line, so it remains unchanged. This demonstrates that points on the line of reflection do not disrupt symmetry. Understanding these examples will help us reason through the problem more effectively. The problem comes with a few constraints and edge cases to consider. First, the number of points can range from 1 to 10,000, and their coordinates are integers between 10,000 and 10,000. Duplicate points may appear in the input, but they don't affect symmetry. For example, a single point or multiple duplicates are always symmetric. If all points lie on the same vertical line, the result is also true. However, if no symmetry exists, such as when points are scattered without a clear reflection line, the result is false. These constraints and edge cases ensure we handle the problem comprehensively across all scenarios. When solving LeetCode problem number 356, the objective is to determine if a given set of 2D points is symmetric about a vertical line. To approach this, one possible strategy is brute force. The intuition behind this method is to calculate a potential vertical line of reflection by finding the midpoint of every pair of points. Then, we hypothesize whether this midpoint could represent the line of symmetry. To verify, we would check if every point in the set has a corresponding reflected point across the hypothesized line. This approach involves three main steps. First, calculate the midpoints for all point pairs. Second, use these midpoints to identify potential lines of reflection. And third, validate symmetry by checking each point's reflection. However, this comes at a cost. The time complexity is n squared, because we need to examine all pairs of points. The space complexity, though, is 1, as no additional storage is required. While straightforward, this method can become computationally expensive as the dataset grows larger. The brute force approach, while comprehensive, is not ideal for large datasets due to its quadratic time complexity. An alternative and more efficient strategy leverages symmetry properties. For a set of points to be symmetric about a vertical line, their x-coordinates must align with their reflections. This means the vertical line of symmetry will always pass through the midpoint between the smallest and largest x-coordinates. Using this property, we can optimize the process. First, we identify the smallest and largest x-coordinates, denoted as min_x and max_x. From these, we calculate the potential line of symmetry as line_x equals min_x plus max_x /2. Next, for each point x, y, its reflection across line_x can be determined as 2 *line_x x, y. To validate symmetry, we store all points in a hash set. Then, for each point, we check if its reflected counterpart exists in the set. This approach significantly reduces unnecessary computations and avoids the need to test all pairs of points. This optimized hashing approach achieves a time complexity of n, as we make a single pass to compute line underscore x and verify the reflections for all points. The space complexity is O(n), because we store the points in a hash set. While this method requires additional space, it scales well for large datasets. The trade-offs here include the extra memory usage, but this is more than compensated for by the linear time complexity, which makes it highly efficient. Ultimately, this approach is both practical and scalable. By focusing on the midpoint between min underscore x and max underscore x, we eliminate the need to consider multiple potential lines of symmetry. Additionally, leveraging a hash set simplifies the reflection check, allowing us to validate symmetry in a single pass. When comparing this to the brute force method, the optimized approach is clearly superior, especially for larger inputs. The key insight, or aha moment, in this problem is recognizing that symmetry can be reduced to a reflection check around a single vertical line derived from the midpoint of min underscore x and max underscore x. This realization drastically simplifies the problem, as it eliminates the need to consider multiple lines or test all point pairs. Another important observation is that validating symmetry boils down to checking the existence of reflected points, which is efficiently achieved using hashing. This insight allows us to focus on the essence of the problem without additional overhead. The chosen strategy, approach 2, balances efficiency and simplicity. While the brute force approach is easier to conceptualize, it is computationally expensive, making it impractical for competitive or real-world scenarios. The optimized hashing approach, in contrast, leverages symmetry properties to achieve linear time complexity with manageable space usage. This makes it the best choice for tackling this problem effectively. The problem line reflection challenges us to determine whether a given set of 2D points is symmetric about a vertical line. In simpler terms, this means that for each point on one side of the line, there should exist a corresponding point on the other side, such that their x-coordinates are equidistant from the line. To tackle this, we start by analyzing the input. The points are given as a list of tuples, where each tuple represents the coordinates of a point. The first step is to identify the minimum and maximum x-coordinates among these points. These values are essential because they allow us to calculate the potential line of symmetry. The midpoint between these extreme x values represents the vertical line that might divide the points symmetrically. This line is calculated using the formula min underscore x equals min underscore x plus max underscore x slash 2, and it serves as the foundation for the symmetry checks that follow. Now that we have the line of symmetry, the next step is to efficiently verify the symmetry of the points. To do this, we use a hash set to store all points. The hash set enables quick lookups, which is crucial for checking if the reflected point of any given point exists. This approach ensures that we avoid the inefficiencies of a brute force comparison. The symmetry check involves iterating through each point in the list and calculating its reflected x-coordinate using the formula reflected underscore x equals 2 asterisk min underscore x x. This formula is derived from the geometric property of symmetry. Once the reflected x-coordinate is calculated, we check if the reflected point, with the same y-coordinate, exists in the hash set. If even one point fails this check, we can immediately conclude that the set of points is not symmetric. However, if all points pass the check, we confirm that the points are symmetric about the calculated vertical line. To further solidify our understanding, let's highlight some key insights about the algorithm. First, the line of symmetry is determined solely by the minimum and maximum x-coordinates. These values dictate the midpoint, which serves as the dividing line. Second, the use of a hash set is a critical optimization. By storing all points in the set, we achieve O(1) average time complexity for lookups, making the algorithm significantly more efficient than a naive O(n²) approach. Third, the formula for calculating the reflected x-coordinate, reflected underscore x equals 2 asterisk min underscore x x, arises directly from the principle of symmetry. If a point, x, y, is reflected across min underscore x, the average of x and its reflected counterpart x must equal min underscore x. To implement this, we use a few key data structures. The hash set stores the points as x, y tuples, and we track variables such as min underscore x, max underscore x, and min underscore x for the symmetry calculations. Together, these elements ensure the algorithm is both correct and efficient. Let's analyze the complexity of the algorithm. The time complexity is O, n, where n is the number of points. This is because calculating the minimum and maximum x coordinates takes O, n, inserting all points into the hash set takes O, n, and verifying the symmetry for all points also takes O, n. The space complexity is also O, n, as we need to store all points in the hash set. Now, let's consider some edge cases. If the input contains only a single point, it is symmetric by definition since there are no other points to compare. For multiple points that all lie on the same vertical line, symmetry is guaranteed because the line itself serves as the axis. Duplicate points in the input do not affect the symmetry check, as they do not change the positions of the unique points. Finally, if any point fails the symmetry check, we return false immediately, as symmetry requires all points to have corresponding reflections. To bring it all together, let's walk through an example. Consider the input points equals 1, 1, minus 1, 1, 1, minus 1, minus 1, minus 1. First, we calculate the minimum x coordinate as min underscore x equals dash 1 and the maximum x coordinate as max underscore x equals 1. This gives us the line of symmetry at min underscore x equals 0. Next, we store all points in a hash set, point underscore set equals 1, 1, minus 1, 1, 1, minus 1, minus 1, minus 1. Now, we check symmetry for each point. For 1, 1, the reflected x coordinate is reflected underscore x equals 2 asterisk 0, 1 equals dash 1. We confirm that minus 1, 1 exists in the set. Similarly, for minus 1, 1, the reflected x coordinate is 1, and 1, 1 exists in the set. We repeat this process for the points 1, minus 1, and minus 1, minus 1, confirming their reflections as well. Since all points have corresponding reflections, we return true, indicating that the points are symmetric about the vertical line at x equals 0. This solution determines whether a set of 2D points is symmetric about a vertical line. The approach begins by storing all points in a set to ensure uniqueness and allow O1 lookups. The algorithm then calculates the minimum and maximum x coordinates among the points to identify the possible reflection line's x coordinate, which is the midpoint of the minimum and maximum x values. Next, the code iterates through each point in the input, checking if its symmetric counterpart exists in the set. For a point x, y, its symmetric counterpart would be 2 asterisk reflection underscore x, x, y, where reflection underscore x is the x coordinate of the vertical reflection line. If even one point does not have its symmetric counterpart, the function returns false. If all points pass the check, the function concludes that the points are symmetric and returns true. This implementation is efficient, with a time complexity of O, n, where n is the number of points, as it processes each point once and performs constant time set operations. It also uses O, n, space to store the points in the set. By leveraging the properties of symmetry and set operations, the solution is both concise and performant, handling edge cases such as duplicate points and points aligned on the reflection line seamlessly. Here, we begin by importing the necessary Java utilities and defining our solution class. Inside the class, the method isReflected takes a two-dimensional array of points as input. The goal is to determine if there exists a vertical line that reflects all the points symmetrically. To handle this, we use a hash set to store unique points as strings in the format x, y. This helps us quickly check the presence of specific points later on. We also initialize two variables, minx and max, to track the smallest and largest x coordinates, respectively. As we iterate through the input points, we update minx and max by comparing each point's x coordinate with their current values. Simultaneously, we add each point to the set. Once the loop is complete, we calculate the potential x coordinate of the reflection line by finding the midpoint between minx and max. This is done using the formula minx plus max /2.0. With this reflection line in mind, we then check if each point in the array has a symmetric counterpart across this line. To do so, we calculate what the reflected x coordinate would be using the formula 2 asterisk reflection x, x. If the reflected point, represented as a string reflected x, y, is not found in our set, we immediately return false, as this means the symmetry condition fails for that point. However, if the loop completes without any issues, it means that every point has a valid symmetric counterpart across the reflection line. In this case, we return true, confirming that the points are symmetric with respect to the vertical line. This implementation is efficient because we use the set for constant time lookups, and we calculate the reflection line only once, ensuring that the solution works well even for larger input sizes. To determine whether the given points are symmetric about a vertical line, we start by storing all the unique points in a set. This allows us to perform constant time lookups when verifying symmetry. For the example input points 1, 1, dash 1, 1, the set becomes 1, 1, minus 1, 1. Next, we find the minimum and maximum x coordinates among the points. Here, the minimum x is minus 1 and the maximum x is 1. With these values, we calculate the x coordinate of the reflection line using the formula min_x plus max_x / 2. Substituting the values, we get a reflection line at x equals 0. Now, to verify symmetry, we check each point's reflected counterpart. For 1, 1, the reflected point is calculated as minus 1, 1, which exists in our set. Similarly, for minus 1, 1, the reflected point is 1, 1, which also exists in the set. Since both points have valid reflections, symmetry holds for this example. Having verified symmetry for the first example, let's analyze a second scenario with input points 1, 1, 2, 2. We again store these points in a set, resulting in 1, 1, 2, 2. The minimum and maximum x coordinates are calculated as 1 and 2, respectively. Using the formula for the reflection line, we find it lies at x equals 1.5. Now, we proceed to verify symmetry. For the point 1, 1, the reflected point is calculated as 2.0, 1. However, this reflected point does not exist in the set, breaking the symmetry. As symmetry fails for this point, we conclude that the given points are not symmetric, and the function returns false for this example. Now, let's consider a third scenario where the input points are 0, 0, 1, 0, dash 1, 0. We follow the same process, starting by storing the unique points in a set, which becomes 0, 0, 1, 0, minus 1, 0. Next, we identify the minimum and maximum x coordinates. The minimum x is minus 1, and the maximum x is 1. Using the formula for the reflection line, we calculate the line's x coordinate as min_x plus max_x / 2, which evaluates to x equals 0. With the reflection line identified, we are ready to verify whether each point has a symmetric counterpart. To verify symmetry for the points 0, 0, 1, 0, dash 1, 0, we start with the point 0, 0. Its reflected point is calculated as 0, 0, which exists in the set. Next, for the point 1, 0, the reflected point is minus 1, 0, and this also exists in the set. Finally, for the point minus 1, 0, the reflected point is 1, 0, which again exists in the set. Since all points have valid reflections across the line x equals 0, symmetry holds for this example. Therefore, the function returns true. To analyze the time complexity of our solution, let's break it down into its individual steps. First, we convert the list of points into a set, which we call point_set. This requires iterating over all the points in the input, and since inserting each point into a set is an average O(1) operation, the total time for this step is O(n) for n points. Next, we determine the minimum and maximum x coordinates of the points using the min and max functions. These functions also iterate over all the points once each, so finding min_x and max_x together takes O(n). Finally, we iterate through the list of points to check the symmetry condition. For each point, x, y, we calculate its symmetric counterpart and check if it exists in the set. The calculation of the counterpart is O(1), and checking membership in a set is also an average O(1) operation. Since we perform these steps for all n points, this part of the process takes O(n). Combining all these steps, the overall time complexity of the solution is the sum of O(n) for creating the set, O(n) for finding the minimum and maximum x coordinates, and O(n) for checking symmetry. Adding these together, we arrive at a total time complexity of O(n). Now let's consider the space complexity. The main contributor to space usage is the point_set, which stores all unique points from the input. In the worst-case scenario, where all points are unique, this requires O(n) space. Beyond this, the algorithm uses a few temporary variables like min_x, max_x, and reflection_x, each of which requires constant space, or O1. Therefore, the overall space complexity is dominated by the storage of the set, resulting in O(n). Comparing this optimized solution to a brute force approach highlights the efficiency of our method. A naive approach might involve iterating through all pairs of points to check for symmetry, which would require a nested loop and result in an O(n²) time complexity. In contrast, the optimized solution avoids such inefficiencies by using a set to enable O(1) lookups and ensuring each operation only iterates over the input once. This improvement reduces the time complexity to O(n). When we analyze the best, average, and worst cases of the optimized solution, we see that the time complexity remains O(n) in all scenarios. In the best case, the points are perfectly symmetric, while in the worst case, no symmetry exists, but the algorithm still processes the points in linear time. This consistency is due to the absence of nested iterations or any higher-order growth factors. Ultimately, the big O complexity is justified by the linear nature of all the operations, confirming that the solution is O(n). In this problem, there are several common mistakes to watch out for. First, failing to account for duplicate points is a frequent issue. If a point appears more than once, it should still be treated as symmetric, so using a set or explicitly handling duplicates is essential. Next, it's important to calculate the vertical reflection line correctly. A common misconception is that this line must pass through an existing point, but in reality, it's determined by the average of the minimum and maximum x-coordinates. Miscalculating this can lead to errors. Another mistake is assuming symmetry only involves x-coordinates. While x-coordinates are crucial, the y-coordinates of reflected points must match exactly as well. Additionally, brute-forcing symmetry checks by comparing all pairs of points can lead to inefficient O(n² solutions, especially for large datasets. Instead, you can use sets to optimize this to O(n). Finally, edge cases like single points, duplicate points, or no points at all must be validated to avoid runtime errors or incorrect results. Now, let's consider some insights that are valuable for interviews. The core concept here revolves around symmetry, which is a recurring theme in computational geometry problems. Leveraging data structures like sets or dictionaries is key for efficiently storing and querying points. Be aware that interviewers may extend the problem by asking how your solution would scale to higher dimensions, like 3D symmetry, or how it could handle other types of symmetry, such as rotational symmetry. Recognizing patterns in these kinds of problems is also important. For example, pre-computing metrics like the reflection line and using hash-based lookups can significantly optimize your approach. Lastly, being prepared to discuss how your solution handles tricky test cases such as empty input, duplicate points, or scenarios where symmetry breaks is often a crucial part of the evaluation process. This problem is also closely related to other computational geometry and optimization challenges. For instance, LeetCode 149, Max Points on a Line, deals with identifying collinear points, which is another problem rooted in geometry. Similarly, LeetCode 252, Meeting Rooms, isn't directly about geometry but involves sorting and interval checks, a concept relevant to calculating symmetry lines. LeetCode 850, Rectangle Area 2, is a geometry problem that focuses on efficient computation with two-dimensional points, and LeetCode 587, Erect the Fence, involves finding the convex hull of a set of points, which is another classic geometry task. Exploring these related problems can help you develop a deeper understanding of computational geometry and refine the skills needed to tackle symmetry-based challenges. Finally, let's examine some alternative approaches and their trade-offs. A brute force approach involves looping through all points and checking if their symmetric counterparts exist. While this is simple to implement, it has a time complexity of O(n²) and is impractical for large inputs. A more efficient method uses sets to pre-compute the line of reflection and store points, allowing you to check for symmetric counterparts in O(1) time per point. This reduces the overall complexity to O(n), but requires additional space for the set. Another option is a sorting-based approach, where you sort points by their x-coordinates and use two pointers to verify symmetry. This avoids using extra space but has a slower time complexity of O(n log n). Lastly, a hash map approach groups points by their y-coordinates and checks symmetry within each group. This method can be particularly efficient when many points share the same y-coordinate, but it adds complexity to the implementation. Each method has its strengths and weaknesses, so the best choice depends on the problem constraints and input size. Great job! Today, we explored the line reflection problem, summarized core concepts, and discussed an efficient approach. Remember to practice similar problems to solidify these concepts. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!